Yes, hi. Hi everyone. Good morning.
Hi, Vipul.
All right, so let us continue with the next discussion. So we have started with the simple machine learning model, which is your linear regression. We have seen how do we feed that model, and we have seen what is a regression line. We have seen what is best fit line, right? But it's not that it's not as simple as it looks, right? The first and very important point is there are certain assumptions that a model needs to follow whenever you're fitting a linear regression, right? So, uh, if you just go to your collab link, uh, before actually fitting a model, our model has to follow these assumptions, and that are very, very important for us. The first and foremost simple question that anybody can expect in the interview is when it comes to your linear regression is assumptions of linear regression. So it is very, very important question, and it's very basic. It's very famous question that you guys can expect in the interview. And while just explaining this particular point, you also need to explain these assumptions that we are going to study in in graphical manner, right? Not only theoretical. You should have an understanding of its significance, like what happens if the assumptions are not followed, right? So the first point is linear relationship. Linear relationship. So what do you mean by linear relationship? Linear regression needs linear relationship between independent, that is your x, and dependent variable. Linear regression is very sensitive to outlier, and it is very important to check the outliers before performing regression analysis. It is very important for a linear regression to check an outlier before performing a model fitting part, right? So what do you mean by this? So the this particular sentence has very simple meaning. Let's say you have only one independent variable, that is marketing budget, and you have target variable, that is sales. So there should be a linear relationship, right? There should be a linear relationship. Means if your marketing budget, if you're increasing your marketing budget, your sales should increase linearly. There should be a linear relationship, right? And linear regression is very sensitive to outliers. It is very important to check the outliers before performing the regression analysis. So as you know, you have to plot box plot to check if we have outliers or not, right? And if you have outliers, you have to treat that outliers first. You have to remove that outliers. Then only you can fit the linear regression model to get a better and desired result, right? That is the first point. So first point is nothing but linear relationship. So it's just like it should have linear relationship between your independent and dependent variable. Simple. So it can be represented by a straight line, right? Simple word. So if you have to take a diagram for this, it should be like this. It should not be. Uh, in the form of curve, right? This is known as linear relationship. This is not a linear relationship. This is not a linear relationship. So we can copy this. We can paste it over here. Or let us create a new sheet over here. Let's rename this as 8 December 2024. We can write down assumptions of linear regression. And we can paste it over here. So that is the first point. When it comes to assumption, it should follow linear relationship, right? So we can take this and we can paste it over here. That is the first point. Second point is it is related to normality. Linear regression requires all variables to be normally distributed, and the error terms also should be normally distributed. Error terms should also be normally distributed, right? Now, what do you mean by this? A normal distribution is nothing but it's a symmetrical around the mean. Whenever you have a distribution like this, 50% on the right hand side of the mean, 50% on the left hand side of the mean, the data is distributed equally. That is known as a normal distribution, right? So what you do is you will plot a distribution of the error terms, and that should be normally distributed, right? So this is a normal distribution. Normal distribution means 50% on the left hand side, 50% on the right hand side. So that is a symmetrical distribution that you have. So the point is your linear regression should follow a normal distribution, and the one more important point is the error terms that you have should also be normally distributed. So what is your error term? So for an example, this is your line, and these are the actual data point. This is your error term. This is your error term. This is your error. This is your error. So this is, let's say, -4, -5, minus, this is +2, +3. So what does it say is, it says the error terms also should be normally distributed. Error term should also be normally distributed. So if you just plot the distribution of the error term, it should also be normally distributed. So 50% error should be on the left hand side, 50% on the right hand side. That is the second assumption, right? Now, the third assumption is related to multi-collinearity that we have not discussed yet. We are going to discuss that in our today's session. But let us write down this point. So there should be very little or no multi-collinearity in the data. And multi-collinearity happens when the independent variables are highly correlated. That is linearly correlated. Linearly correlated with each other. So what do you mean by this? What do you mean by multi-collinearity? We'll discuss this in today's session. So you can wait for 5 to 10 minutes. That is what we are going to start in today's session. But I'll just explain in simple word what is multi-collinearity is. It means the correlation of different independent variables with each other. What does multi-collinearity indicates? The correlation of the independent variables with each other. So for an example, you have car MPG here, And you have several other variables like car cc, its weight, and number of gears, and let's say its v engine or other engine. So this independent variable should not should not be correlated with each other. For an example, this cc and weight, if you find a correlation between them, if you find a correlation between them, it should not be high, right? To be more precise, it should not be 30%. Should not be more than 30%. 30% is allowed, but more than 30% correlation between different independent variable is not allowed. What will happen is it will suppress the effect of predicting your target variable because these variables are correlated with each other, right? So you cannot distinguish the effect of cc that has cc it has with the mpg, right? Because cca and weight has a high correlation, so you cannot distinguish your effect of only cc with your target variable, or you cannot distinguish your effect of only weight with respect to your target variable. So if it is highly correlated, that is also a problem, right? That is what multicollinearity is. Now is it clear what is multicollinearity, everyone? Because this is a very important concept. Is this thing clear? Yes, guys.
Can you explain one more time, Apple?
Yes, yes. Just give me a minute. See, what is multicollinearity is, uh, as of now, just remember this or just understand this in very simple words. We are going to see its effect and how it will affect your analysis or your performance of the machine learning model in let's say after some time, right? But what is multicollinearity is, it's a statistical phenomenon in which two or more variable in a regression model are dependent upon the other variable in such a way that one can be linearly predicted from other data with a high degree of accuracy. Now this is also very uh, technical explanation. This is very simple. See, it's a statistical concept where several independent variables in a model are correlated, right? So, for an example, as I've given the explanation, like here, what is your target variable? It's mileage per gallon, right? And what do? You use cylinder displacement, HP, weight, acceleration, year, origin, and car type to predict your target variable, right? Now, if this two variable has high correlation between them, right? High correlation between them. So can you just uh, means it is highly correlated. If cylinder is increasing, your displacement is increasing, and if cylinder is decreasing, your displacement is also decreasing, right? So it's a correlation. They have high correlation between them. So what will happen is, if you just consider this two independent variable and fit a model by using this two independent variable, you will not be able to separate its effect. Let's say cylinder has, you'll not be able to get the individual effect of cylinder to predict your target variable, right? So that becomes your problem. Don't worry if it is not understanding. We are going to spend a separate time on this particular topic. So if it's still not clear, don't worry about that. We'll just see this after some time, right? So there are different methods to calculate or detect the multicollinearity. This is also something which we are going to discuss after some time. First is you have to plot correlation matrix or heat map, which we have seen in our data visualization session, right? Then we have VIF with us, which is known as variance inflation factor, which detects the multicollinearity. So what you do is you find the VIF by using a formula. VIF is equals to 1 divided by 1 minus r squared or r2 score, right? And if the VIF, there is no any standard rule to follow what should be a VIF value, but it is observed that if VIF is greater than 5, we conclude that there is a multicollinearity in the data, right? So some uh, people follow this notion of taking VIF greater than 10, but that's not a hard and fast rule. If VIF is greater than 5, it means it is a serious problem, right? And some people will follow this notion of following the VIF is greater than 10, then there should be a multicollinearity, right? But if you just go in ground level, there is no any hard and fast rule to consider the VIF value. But I'll suggest to consider VIF, it should be greater than 5, and then there is a multicollinearity in the data, right? To be on the safer side. And the fourth assumption that we have is related to homoskedasticity. This is also very important. The error terms must have a constant variance with respect to the regression line. The error term must have constant variance with respect to regression line. And this phenomenon is known as homoskedasticity, right? The presence of non-constant variance is referred to as heteroskedasticity. And last but not the least, it is autocorrelation. So it says there should be no correlation between the residual, that is your error terms, and absence of this phenomenon is called as autocorrelation, right? So there should be no correlation between the residual terms. We'll discuss these 2 points separately. The first point is related to homoskedasticity, and what is that? We'll just take that. So what it says is homoskedasticity means the error term must have a constant variance with respect to the regression line. So suppose this is your regression line and these are the errors, right? 1, 2, 3, 4. This is your data point, this is your error. Again, this one, and this one. So when it comes to error terms, these are your error terms, it should have a constant variance. So if you just plot a variance, if you just see a distribution of a variance with respect to a regression line, it should be a constant. So it should not increase as you increase your x values, right? It should not increase as you increase your x value. So as the x increases, your variance should not increase like this, variance of the error terms, right? So homoskedasticity, if you see a diagram, suppose this is your regression line and these are the data points, right? So if you just plot a spectrum of error terms, is it a constant with respect to regression line? It's not a constant, right? Here it is constant, it is increasing now, your error terms, right? But when it comes to this point, your error terms are constant with respect to your regression line, right? As you're increasing x, your error terms are not increasing. Yes or no? Here also, if you increase your independent variable, if you just draw if you just see a spectrum of this, your error terms are not increasing. It's a constant throughout the regression line, right? But in this case, suppose this is your regression line. Is it a constant error terms? Here it is this much, but here it is very high, right? As you're increasing your x value, your error terms are high. But here, if you just plot a regression line, it's a constant throughout the regression line, right? Are you guys getting this point or not? Yes, everyone. Can I get a confirmation? Or if you're not getting, just ask,
Yes, sir.
right? This is very important point because what do you mean by variance basically? I'm just asking very basic question. What do you mean by variance? So suppose this is your mean and this is your distribution of the data, right? So variance is the average square distance of each data point with respect to mean, right? It's a distance with respect to mean, right? Or distance with respect to any particular terminology, right? So here we are calculating variance with respect to a regression line, right? So suppose this is your regression line. These are the distance, average square distance of each data point with respect to regression line. So it is not a constant, right? When we say it as a constant, if it is constant throughout, if the distance is not changing with respect to regression line, right? Distance of what? Distance of error terms. The error terms must have a constant variance with respect to regression. Now, I think I have given enough time on this. If it is not clear, you let me know. We can discuss it after some time. Now let's move towards the autocorrelation. Autocorrelation, if we have to see it in very simple uh, term, we can consider autocorrelation like this. So suppose there is you are working in a, let's say, umbrella shop, and for Jan your sale is 100. For Feb, sale of the umbrella is 110. For March, it's 120. For April, it is 130. For January, February, March, April, May, it is 140. If I ask what will be a sale of June, you can easily answer. What is that answer? What will be the sale of June?
150.
Right. So this is known as autocorrelation. There is a relation between your what we can say previous term. This particularly works well with the time series data, right? So I'm just giving one notion over here. If you are working on time series model, we should have autocorrelation. We should have a correlation like this, right? But what does your linear regression says? There should not be autocorrelation between your residual error terms. So suppose these are the error terms that you have. So it should not be correlated, right? For an example, if the first error term is 100, second is 110, then it's 120, 130, 140. It should not be autocorrelated. There should not be a correlation between them, right? Because we already have seen this point, there should not be a correlation or correlation between your different independent variable, that is your multicollinearity. This also has the same point. There should not be correlation between the residual error terms. So if any of these points, any of this uh, assumption is not followed, then you can expect the significant drop in the accuracy, right? So it is very essential to check these assumptions before fitting your linear regression model, right? And this carries a lot of weightage in your interviews. So this should be a very important point You should mark this as your important one if you are preparing for your interviews, right? Or if you are making a notes. Now, is this thing clear to you, everyone? So this summarizes your entire linear regression uh, model, right? Now we have discussed this. Um, Now what we'll do is we will try to understand a simple linear regression model, a very simple one, right? Earlier we have discussed how do we fit multiple linear regression model. You already have got familiarity with that. Now what we'll do is we'll just take a simple linear regression model and we'll try to fit that by using two techniques. So the first one is your, just a minute, let me create a new folder, day 19 8th December, linear regression. And here you guys will require a data, so I'll just upload that. Advertising this one. And we'll create a new Colab notebook. And what we'll do is we'll create a new. What do you prefer, guys? If I just add everything related to machine learning, same folder, or we should create separate Google Sheet for each day? What do you prefer? What will you suggest? We should have a single Google Sheet, or we can have different for each day. What should we do? Single itself will be fine, I think, because in single sheet itself, we'll be able to revise each and every topic, right? Rather than just having it in separate folder, right? Let's do single now. So this is 8 December. What we will do is, there are two libraries that we can use to just fit the model. I'll just tell you. First, we already have discussed sklearn. By using sklearn, we can easily fit the model, and everybody knows that. Second is stats model, and there's no any difference in these two libraries as such, but stats model will give you more statistical analysis, or more statistical terms in the analysis, right? So it is widely used. It will not be wrong to say it is widely used by statistician's favorite library, and sklearn is used by ML engineers out there, right? So whenever uh, you will find stats model, you will, or if you use stats model, you will get a lot of statistical terms that are uh, preferred by statistician people out there, right? So we'll just try to study a stats model library now, right? So what we'll do is quickly upload the data that we have over here. We'll just quickly upload the data. And if you want to do this simultaneously with me, you can do. But remember, you should focus on this. So if it is not, I mean, if you're not comfortable with doing simultaneously, it is suggested for you to just study this as of now. So what we'll do is we'll import warnings, and we are going to filter warnings, as we already have discussed. How do we filter warnings? Filter warnings in quotes, ignore. And we'll just write down step by step, like what are the different steps of any machine learning model building part. So this is simple linear regression. Here we'll be dealing with only one independent variable. So the step one is always will be reading and understanding data, right? So in that, the first step is importing data using the pandas library and understanding the structure of the data. Now, what we'll do is we will import the libraries, import the libraries, import pandas as PD, import numpy as np, and we are going to read the CSV file. So let's call it as advertising is equals to PD dot read underscore CSV, and you have to copy the path and you can paste it over here, right? And if you just check what is there in this data, so we have TV, we have radio, we have newspaper, and we have sales of the that particular organization. So if you just take TV and feed the model, this becomes your simple linear regression, right? Just by considering a one independent variable, right? Here we have three independent variable. That becomes your problem of multiple linear regression. But anyway, it's fine. We can uh, take uh, a single independent variable as of now and just try to build a simple linear regression model, right? Before that, we can check the shape of the data, which is advertising dot shape. We can check information of the data by using info function to check if we have any null values in the data or not. We do not have null values, right? And we'll check descriptive statistics of the data, right? Now, step two can be your visualizing the data. Simple. Now let's now visualize our data using Seaborn. We will first make a pair plot of all the variables present to visualize which variables are most correlated to sales. So we'll import matplotlib.pyplot as plt, and we'll import cbod as SNS, right? And we'll do a pair plot of the data advertising. And in pair plot, what you can pass is you can pass this much uh, argument. You can pass HUE, palette, X variables. So let's pass X variables over here. Let's take this X variables, and X variables I want on X-axis, I want TV, radio, newspaper. On Y variable, I want sales, right? Height is not needed. You can do that, but I'll write down size equals to 4, aspect is equals to 1, and kind. What do you want in pair plot? You want scatter plot, and you'll write down plt.show. So if you do this, you'll get a scatter plot consisting of this 3 variable on X-axis, and Y-axis will be sales, right? So you can see TV has got a good graph, right? because radio scatter plot is very if you just take uh, what we can say a variance of the error terms with respect to regression line, it is not a constant, right? If you just plot a variance, suppose this is your regression line, so it is here, then decreasing, then increasing, right? But it can be constant over here. This is constant. Here also it is very highly scattered, right? So this is also, this does not have the constant variance. So that is what can be concluded from this scatter plot. And if you just go with the heat map, you'll understand the correlation between all the variables out there, right? So this is just a normal heat map, but if you want to add a color, so you'll write on C map is equals to yellow L G N B U. This is L, I think. Yeah. And annotation is equals to true. Means you want numbers over there, right? The correlation value. And how do you read this? Is the correlation between TV and TV is 1. Correlation between radio and radio is 1. Correlation between newspaper and TV is 0.057. Correlation between TV and newspaper is again the same thing. Correlation between radio and newspaper is 0.35, right? So this is your correlation. And as I told, it should be always less than 30% between independent variables with each other, right? In order to avoid the multi-collinearity in the data, right? So the correlation between TV and radio is this. It is good. But if you see correlation between TV and sales, it is 90%. But that is a target variable, right? You want to check the correlation between two independent variables. So here radio and newspaper is somewhat problematic. But apart from that, all are good, right? All the independent variable has very less correlation between them. So what can be a conclusion for this graph is, as it is visible from the pair plot and the heat map, the variable TV seems to be most correlated with sales. So let's go ahead and perform simple linear regression using TV as our feature variable, right? TV has a high correlation with respect to your target variable, that is your sales. So let us perform a simple linear regression, right? And the reason why we are doing this is we wanted to see the stats model library, right? So as you know, the equation of a linear regression is can be written down as y is equals to m1x1 plus m2x2 plus dot 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 plus mnxn. Y is the response variable, that is your target variable. C is the intercept. M1 is the coefficient for the first feature. Mn is the coefficient for the nth feature. But in our case, as it is a simple linear regression, we'll write on M1 into TV, that is your x variable, independent variable, plus C, right? The M values are called as model coefficient or model parameters. The M values are called as model coefficient or model parameters, right? Now we'll follow a generic steps in model building by using stats model. Generic steps in model building using which library? Stats model library, right? Here the steps are same. We first assign the feature variable, that is TV, in X, and in Y you have target variable, that is your sales, right? So X is equals to advertising. Which variable you want? TV you want, right? And Y is advertising. Which variable it is? Sales it is. Right? Now, what we have is same thing. We have to do a trend test split. So we'll go with the trend test split. And here also, it will require a library. So from sklearn.model underscore selection, import trend underscore test underscore split. Now here I know this thing, but what if you don't know a package? So what I told is you have to go with the official documentation of sklearn, and you can copy the package from this, right? Now how do you do? It's time to go with the trend test split. Everybody knows this. X train X test, Y train Y test is equals to train underscore test underscore split, the package name. In that you need to pass X comma Y comma train underscore size is equals to 0.7. This is also fine, or you can, if you write test underscore size, that is also fine. So you don't need to specify train size if you are specifying test size, right? And random state, we'll discuss that in today's session. As I told you, we are going to discuss this random state in today's session. But before that, did you revise this, or did you research about random state? Anybody? Have you gone through this topic, random state? Yes, everyone. I knew nobody will revise. So if you just check your head of the data, or if you just check shape of the data, not head, you'll find that we have 200 records, right? So suppose this is your data in which you have 200 records, right? Now, if you don't specify what is random state is, uh, it will not save a specific combination of train and test. So for an example, here test size is 0.3, train size is 0.7. So I can say 70% data is in train set, right? 30% data is in test set. Yes or no? So suppose these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose these are 200 data points. Out of this 200, let's say if you write down random state is equals to 1. So for a particular random state, you don't have an understanding of what happens in the background. But just take example for random state 1. This first 7 will be a part of your train data, right? And this will be a test. So it will make a combination and it will fix that, right? And if I run this again, if I restart and run all the sales, it will not change the combination, right? By using this random state, it will log that particular combination, right? Now see what happens if I just don't give random state. What we'll do is we'll quickly load the data. We'll just load the data and I'll not provide random state. See here, uh, after providing random state is equals to 42, the combination is locked. Certain combination is locked. Your accuracy that you are getting for the specific model or the R2 score is 0.8641, right? As the combination is locked, it will not change. Even if I restart and run all the cells, right? Even if I restart this and run all, my R2 score will not change, right? It will be 86.41 for all the iteration or all the times, right? 86.4. But if I just don't provide the random state, what will happen is it will not lock any combination, right? Random it will take. If I restart and run all, in the first iteration, you will get some different R2 score. In second iteration, as you're not fixing this combination, it will give you another R2 score. See, now this first iteration, you are getting 77.47, right? As we have not specified the random state, if I restart and run all this 77.41 will be, or 77.47 will be changed, right? 77.47 will be changed. It will change. 82.12. Again, if I restart, 82.12 will be changed. Right? It is not a fixed. So every time the accuracy is not in your hand, right? Every time you run this sale again and again, the accuracy is not in your hand. So it is very, now it is 82.65, right? Again, if I restart and run all this, it will change. So what is happening is, as you have 200 data, can you imagine 200 data will be very, very large, yes or no? And for that 200 data, to make a combination of 70% data will be in your training set, 0.7 into 200. 140 data points will be in the train as part of your training set. So that can be any 140, right? It can be first 140 or it can be this and then. So you can imagine what type of combination it can be, right? So there is no any rule of uh, adding a random state value. First point, you can give any random state, and there is also no any specific value of a random state. It can be anything, 1000, 42, 52. It can be anything, and it is just an experimental procedure that after, let's say, if you provide your random state is equals to um, suppose if it is 3, if you write down random state is equals to 3, and you'll see that your accuracy is uh, let's say 90%, right? So it's just a trial and error method, but it is advisable to not spend much time on just uh, trying the combination of random state, because that is totally random, right? You do not have any control of the accuracy over there. Instead of this, we have several other methods to increase the accuracy. So we'll not be actually spending more time on just trying the random state combination over there, right? So for random state is equals to 3, it is 82.62. Now we'll just try another random state. Let's say random state is equals to 1. And just try to fit the model. Now it is 85.82, right? So it is advisable to not spend more time on this. You just initialize your random state and that's all. And what it will do is it will lock a combination. So if you restart this particular notebook, and if you, even though if you restart and come after some days, your accuracy will not change. That is certainly locked over there. So the combination is locked, right? So that was all about your random state. Now let us move back to the stats model library over here, as we have done 70-30 split. So if you just check x underscore train dot head, it will be 0.7 of 200. That will be uh, how much data? I think 140, right? Oh, shape is not callable. You don't need to have 140 data will be in the training set, and one uh, remaining 60 will be your part of the test set, right? Now it's time to build a linear model, but not by using sklearn. You first need to import the library stats model dot API library, and using which you will perform the linear regression. So let us import that using stats model dot models dot API as SN. This is a standard procedure to import the library. And by default, stats model library fits a line on the dataset which passes through a origin, right? So even though if you have an intercept, it will not assume that. By default, it will pass through the origin. Always remember this point. So I'm just writing down this point. By default, the stats models library fits a line on the dataset which passes through the origin, but in order to have an intercept, you need to manually use the add underscore constant attribute of stats models. And once you have added constant to your x underscore array dataset, you can go ahead and fit a regression line using the OLS, that is ordinary list square attribute. So by default, it will pass through the origin, but in order to have that intercept, the C value, you need to manually add constant attribute of the stats model. So we'll just do that, right? So if you ask me, like why we are doing a add constant to get an intercept, you should be able to understand why we are adding the add underscore constant. So that is your C value of the X string, right? And then we are fitting the regression line using OLS method. So just object fitting, object creation and model fitting at the same time. sm.ols, that is known as ordinary list square method. It is it is an attribute or a method in your stats model library to fit the regression line, right? And then what you'll do is you'll print the parameters. That is your equation of a straight line. That is the intercept and the slope of the regression line fitted. So I'll write on lr dot params. So constant is this, TV, C value is this, M value is this, right? This is M, this is C. So if you have to predict your Y, it will be 0.054 times TV plus 6.9486. By default, if you don't add a constant, it will be 0, right? It will be passed through the origin. But that is not the case, right? We have seen this. In your pair plot as well, if you just see your regression line is not passing through the origin. Suppose if you plot a regression line, it is not passing through origin, right? So that is what we have. Now it's time to perform a summary, and you'll understand why I told you that this library is often preferred by all the statisticians out there. So performing a summary operations, list out all the different parameters of the regression line fitted. You'll add an lr dot summary. It will give you all the summary out there. And in that, most of the terms are statistically significant. R squared, adjusted R squared, F statistics, probability of F statistics, log likelihood, AIC, BIC, right? Number of observation, residuals, degrees of freedom of the model, covariance. It's not needed for you, right? What is important is this probability of F statistics, your R squared, adjusted R square, and probability of this constants. Simple, that's all. It's not needed for you at this point of time, this rest of the things, right? So I'll just tell you two important terms. R squared is 0.816. What does it mention is, it specifies that 81.6% variance in sales is explained by your TV, because we have taken only simple linear regression. In that we have TV and we have sales, right? As I told you, R square is an indirect indicator of your accuracy, but in more technical term, it gives you what amount of variance is explained by your independent variable to predict the target variable, right? So you can write down that. And rest of the things are explainable. So what we'll do is to just understand the stats model analysis, I'll write down few key important points. Key statistics from the summary. So the first point, the values we are concerned with are the coefficients and significance, that is p values. Second is R squared. Third is F statistics and its significance. So the first point, the coefficient for TV is 0.054, as you have calculated over here as well, or this one, right? So its probability is very low, 0 point something. So the association is not purely by the chance. Now this is a little advanced for you, but is not needed. But you can have this. It is not purely by chance. Second point is R squared is 0.816, meaning that 81.6% variance in sales is explained by your independent variable, that is T. And third important point is F statistics has a very low probability value, that is practically low. It should be low. Low is desired, meaning that the model is statistically significant, right? And the explained variance isn't purely by chance. So the fit is significant, and let's visualize how the model fit the data, right? So I can write down this equation from the parameter sales is equals to, that is y is equals to m1 into tv plus c. So it becomes 6.948 plus 0.054 times tv. That is the equation. So what I'll do is I'll plot a scatter plot between x train and y train, and I'll add a line plot between x train and this equation of my uh, regression line, which is 6.948 plus 0.054 times x underscore train. And the color that I want for a line is red, and I'll write on plt dot show. So here train should be there. So this is your line plot, and this is your scatter plot. This is your equation of a regression line, and you will be able to see that this regression line is fitting, how this regression line is fitting to your particular data, right? And you can validate the assumptions that we have seen by just plotting your distribution and check if the error terms are normally distributed or not by using figure is equals to plt dot figure sns dot dist plot residual comma bins is equals to 15 figure dot subtitle is error terms comma font size is equals to 15 plt dot x label y underscore train minus y underscore train grade comma font size equals to 15 and plt dot show. Residual is not defined. Okay, we need to define this. We'll write on y underscore train underscore grade equals to lr dot predict x underscore train sm residual is equals to the difference between y train and y grade. So the residual terms are normally distributed, yes or no? 50% on the left hand side, 50% on the right hand side, with mean is equals to 0. So that becomes your standard normal distribution. Not only normal distribution, standard normal distribution, right? And rest of the assumptions that we have when it comes to homoscedasticity, you can check that. And now what we'll do is we will predict the data, right? So I can put heading as fifth point as the predictions on the test set. Now that you have fitted a regression line on your trained data set, it's time to make some predictions on the test data. For this, you first need to add a constant to the X test as well, because uh, as you have seen, your ordinary least square method or stats model does not take care of the constant, right? So you need to add a constant to the X underscore test data, like you did for X underscore train, and then you can simply go on and predict the y values corresponding to X underscore test using the predict attribute of the fitted regression line, right? So we'll add a constant to your X underscore test. We'll write an X underscore test underscore sm is equals to sm dot add underscore constant, and you'll predict the y values corresponding to the X test by using predict model. And if you just check predicted data, it will look like this. And if you just check y underscore test, it will be this, right? So first it was 6.6, it is 7.37, model has predicted. Second, it is 19.94, model has predicted 19.94, it is 20.7. Third data point, which is 99, it is 14.32, it is 17.2, but model has predicted 14.32, right? Now it's time to calculate the RMSE and R2 score for this model. So rest of the things are same. From sklearn.metrics, you'll import mean squared error. From sklearn.metrics, you'll import R2 score. And looking at the RMSE, you'll find np dot square root of mean squared error between your X test, Y test and Y pred, and you'll check R2 score again between Y test and Y pred. That becomes a 79.21. That is not a bad, right? And now just try to visualize the scatter plot between your X test and Y test, right? Earlier we have done scatter plot for your train, right? Right? This is your actual data. This is your predicted data. Between that, you have fitted the model. Now, again, here we'll plot the scatter plot for X underscore test and Y underscore test. And the equation of a line remains same. And it is quite good, right? So this is your X test. This is your actual data, basically. This is your actual data. And this is your regression line for the model, right? So that summarizes your linear regression by using stats model library. Only thing that you need to remember is uh, you need to add a constant, because by default your stats model library will pass from the origin. So you have to write an add underscore constant. Is it clear now till now? Here, till this point, do you have any questions? Yes, everyone. Do you have any questions, guys? So the steps are very similar. X test. Okay, you need to add a random state, right? Let's add 100 as the random state and then try to do this. So steps are very similar. First of all, you have to do the trend test split. Then you have to uh, create, add a constant, fit the model, check the parameters. Summary will give you everything related to R square and whatnot. And you can plot the scatter plot between X trend and Y trend and just plot a regression line on that. And you can check the error terms residual. You can find the R2 score for the test data, and you can fit the regression line. So this is also very similar and easy. Only thing is you just need to write down you need to add a constant. That's all. So here also we have added a constant if you just see, right? Where does that uh, 6.948 value come from for the PLT dot plot? 6.948 value we already have calculated, right? This is your equation of a line, right? Regression line. So we have used that equation of a regression line. So it y is equals to mx plus c, right? Y is sales. M is your TV constant, that is 0.0545 times TV plus C, right? C is 6.948. So that is your equation. Now you go through this. We'll take a break for 10 to 10 minutes at least. And after the break, we'll see the next part. Just go through this notebook one more time. Okay, so it's 10:19. We'll have a 12 minutes of break. Just have break till 10:31. All right, so let us understand the multiple linear regression. Then why there is a need of multiple linear regression? So, so far we have discussed the simple linear regression where the model is built using only one independent variable, right? But what if you have multiple independent variables? How do you make a predictive model in such a case? So what we do is we build a multiple linear regression on the top of such a data is a one such solution, and we can take the same example of that particular data. We can take the same example wherein we have TV, newspaper, radio, right? So instead of just one variable, you will have three variables to deal with. The marketing budget will be split into three marketing channels like TV, radio, newspaper, and you'll see adding more variables brings in many new problems. And how do you approach them? So adding a new variable is not the same. Where is- Just a minute. Yeah. So simply adding a new variable is not the same. Simply adding a new variables will not uh, be easy, right? Uh, Adding a new variable has a lot of problems, many new problems associated with them. And how do you approach them? This problem will just try to understand that. One of the problems that we have is multi-collinearity, which we already have discussed. Now we'll discuss this in more detailed manner. And in the end, we are going to discuss feature selection and feature elimination to build the most optimal model, right? So this session is completely a theoretical one on multiple linear regression and its various aspects. So you don't need to worry much if you don't get everything in the first go, as you will also see each of these theoretical aspects in practical implementation in Python and Python demonstration, where things will become more clearer, right? So as of now, we'll just touch this topic theoretically. If time permits, we'll discuss this in more practical manner, and at that time it will become very simple for you, right? So the first thing is motivation when one variable isn't enough for you, right? The term multiple in multiple linear regression gives you a fair idea in itself that it represents the relation between two or more independent input variables and a response variable. Multiple variable is needed when your one variable might not be sufficient to create a good model and make accurate predictions, right? So that's what our motivation is when your one variable isn't enough to give you an idea about that, to give you a more accurate result, right? So let us take this example of your um, simple linear regression pair plot. Let us take this and let us paste it over here. Right now, uh, what do we have is We have TV, we have radio, we have newspaper, and its scatter plot. Now, uh, what we have done is, suppose we have we have calculated the R squared for each and every individual simple linear regression model, for TV, for radio, for newspaper. R squared is 0.816, this is 0.112, and this is 0.058. So the TV has the highest R score, right? That's why we have chosen the to go with the simple linear regression model by only considering TV, right? But the idea is, what happens if we club uh, this three models together, right? What happens? That's what the motivation behind the multiple linear regression, right? So suppose if I just take TV plus linear, if I just build a multiple linear regression model on TV and newspaper, my R2 score is coming out to be 0.836, and TV plus radio, it is 0.910. So if you just combine TV and radio, you'll be able to explain your variance of the data, or you'll be able to, your TV and radio independent variable will be able to explain 91% of the variance of the target variable, that is sales. So why should not we use this, right? Why only we go with the 0.816? Why should not we go with 0.91 0.91 R squared, right? So that was the idea behind the multiple linear regression, to club the multiple variables at a time, right? Now, you saw multiple linear regression will be useful in creating the better model. And as there was a significant change in the value of R squared, from 0.816 to 0.91, right? So it seems that adding a new variable helps to explain the variance in the data better, right? Now it is also recommended that you check R squared for for after adding the variable, right? After adding the variable, you should check that. Check R squared to see how much the model has improved, right? And the formulation will now will change. It will become y is equals to m1 x1 plus m2 x2 plus m3 x3, and so on. And apart from this calculation, there are some other aspect that still remains the same. Uh, the model now fits a hyperplane now, right? What do you mean by hyperplane? As it is a two-dimensional, we have two dimensions at a time, so it will not be a your it will not be your two dimension, it will be three dimension, right? Where uh, this dimension will represent, let's say, TV, this represents radio, so this third dimension will represent your uh, sales, right? So basically it will not be a line, it will be a plane, right? The model now fits a hyperplane instead of a line. Second point is coefficients that we have are still obtained by minimizing the sum of squared errors and the least squares criteria. The third is for interference. The assumptions from simple linear regression still hold same. So all the assumptions will be same for simple linear regression, right? All assumptions will be same. So these are the three important points that you need to take care. And there are still few other considerations that need to be made when moving from simple to multiple linear regression, and let us discuss them in the next segment. So moving from uh, your simple linear regression to multiple linear regression, there are new consideration that you have to consider, right? So we'll just take this, we'll write on fifth, change the font and this bold. So moving from simple linear regression to multiple linear regression. So when moving from simple linear regression to multiple linear regression model, there are few things that you have to look at. First is, it is a problem of overfitting. As when you keep adding new variables, the model may become far too complex. It may end up memorizing the training data and will fail to generalize. Then a model is generally said to overfit when the training accuracy is high while the test accuracy is very low, right? Then you have multi-collinearity, that is, as we have discussed, association between different independent variables, which you will study later. And there's a problem. There's a thing which is known as feature selection. What you have to do is you have to select optimal set from a pool of given columns or features, and many of which might be redundant, and that becomes important task. So as you know, in this problem you have cylinder displacement, HP, weight, acceleration, year, origin, and car type. So what do you think, all the columns will be important for us, or only some columns will be important for us? Obviously some, only few columns, let's say these four columns are important and it has a feature importance. So we need to find that and we need to eliminate these features which has redundant or which has less importance, right? So this particular procedure of selecting only important feature and discarding least important feature is known as feature selection, right? And it is also a very important part that we are going to discuss separately in the upcoming sessions, right? So what do you mean by feature selection? We just select a set of set from a pool of a given features which has high importance rather than low importance, right? And to just give you an idea about what overfitting is, because this will be your famous interview question, it simply means that your training accuracy will be high, but if you just try to check your accuracy on the testing data, testing accuracy will be poor. So in very simple words, it means there is a need of very simple model. There is a need of very simple model, but unnecessary you have made your model complex, right? Simple model was needed over here, but you have used a complex model. So it is trying to it will fail to generalize well on your unseen data, that is your test data, right? That is known as overfitting. And what is underfitting? There's concept of underfitting as well. I'm just giving you a hint, just a trailer of this overfitting and underfitting, because that is our uh, separate topic that we are going to discuss. Here, your training accuracy will be poor, and your testing accuracy will also be poor. So both the accuracy are poor, and here it means there was need of a complex model, but you have fitted very simple model on that particular data, right? So these two terms are very, very, very important when it comes to your machine learning or when it comes to your interviews, right? So you can take this figure and you can refer this to understand what the overfitting and underfitting is, right? Anyway, we are going to touch this topic separately. Now, there is a, as we have discussed, there is a problem of multi-collinearity. And what the problem is. So it refers to the phenomenon of having relation between the independent variables. In simple terms, in a model which has been built using several independent variables, some of these variables might be interrelated, due to which the presence of that variable in the model is redundant. And you drop some of these related independent variables as a way of dealing with the multi-collinearity, right? So how it affects your data? It affects in two ways. First is interpretation. Uh, so does change in your y when all others are held constant, does it apply? And inference, coefficients swings wildly, signs can invert. So therefore, the p-values are not reliable, right? This is a statistical part. I'll just tell you an importance of p-value is. What importance of p-value is. Your stats model will give you an idea about the statistical terms, right? There itself you have calculated the probability value, and which is coming out to be less. So if you have multi-collinearity present in the data, your p-value is not the significant one. So you basically cannot take decision based on your probability value, that is a p-value, right? So even though ideally your p-value should be less than 0.05, then we say that the model is statistically significant. And here it is very, very less, so that is a good model for us. But if you have multi-collinearity in your multiple linear regression, and even though if you use stats model library, your probability is coming out to be very less, which is less than 0.05, but still that is not a reliable value. Because uh, there's a problem of multi-collinearity, right? So that's what they are trying to say over here. So these p-values are not reliable to take up the decisions. right? So there are these two problems, and thus the multicollinearity is a big issue when you are trying to interpret the model, and is also essential to detect and deal the multicollinearity present in the model. And let's see how do you detect that. So as we have discussed, uh, how do you detect multicollinearity? There are two ways. First way is to plot the correlation matrix and heat map and just check the correlation between different pairs of independent variables. And second is, that is very, very widely used, and it's a clear cut sign of indicating your multicollinearity, that is variance inflation factor. So the pairwise correlation is not enough sometimes. Instead of just one variable, the independent variable might depend upon the combination of other variable, and we have to calculate how well the independent variable is explained by all the other independent variables combined, right? This formula is 1 by 1 minus r square. And as I already have discussed, there is no any hard and fast rule. If it is greater than 10, it is definitely high. Multicollinearity is definitely high, and variables should be eliminated. If it is greater than 5, it can be okay, but I personally don't use greater than 5 as well. For greater than 5, I considered it as a warning, right? So even though they say theoretically if the VIF is greater than 10, then we should eliminate the feature, but it is worth inspecting the multicollinearity and remove that if you get where your VIF greater than 5, right? And less than 5 is good, actually. Good VIF value, no need to eliminate this variable, right? And once you have detected the multicollinearity present in the data, you have to deal with that. Uh, there are several ways to deal with the multicollinearity. First way is you can directly drop variables. Drop the variables is high, which is highly correlated with each other. Which is highly correlated with each other, and you can pick the business interpretable variable. Second is creating new variable using the interactions of the older variables. So what do you do is you add interaction features, that is features derived using some of the original features. And third is variable transformations. We go with the PCA. That is a separate topic which we are going to see at the end of the machine learning module. That is known as principal component analysis, right? So these are the three ways in which you can deal with the multicollinearity. Depending upon the business problem, like for an example, uh, it's totally based on your uh, interpretation of business uh, problem statement over here. Suppose you found that your cylinder displacement HP are good, but weight, acceleration, year, and origin has a lot of multicollinearity in the data. Right? This variable causes multicollinearity, right? But what you'll do is, what you will go and check your problem statement. What is the problem statement? We have to predict the mileage of a car. So what you'll do is, you will try to understand if there will be a loss if I drop weight, loss in the data if I drop weight of the car, right? If I drop weight of the car, will there be any loss? Yes, because weight is highly proportional to mileage, right? If the weight is high, if weight is high, then mileage obviously will be less. Yes or no? This year does not make any sense. So you can remove that, but it's totally depend upon the expertise that the user has when it comes to business uh, problem statement, right? So depending upon the data set, you need to go and actually spend some time analyzing which variable is important. If I drop that, then there will be any loss of information of the data, and then you can go ahead with the dropping that particular variable. So that's what the pick up the business interpretable variable means, right? Second is, you need to create a new variable using the interaction of the older variable, that is features derived using some of the original features. Uh, so what do you do is, you'll do some transformation and create a new variable by using some older variables, right? That's what it is. And then there is a variable transformation, that is PCA for us. So theoretically we have discussed PCA, and this is very important topic. That's the reason I have given more emphasis on this particular part. If it is clear, that is good for us, but if it is not clear, you don't need to worry. We are going to see this practically, right? How do you remove the multicollinearity? But there was a special uh, reason why I have given more weightage to this particular part, because this is very, very important when it comes to your interviews, right? So multicollinearity, overfitting, underfitting, and this thing, like what is multicollinearity is, how do you detect multicollinearity, and how do you deal with the multicollinearity is very important for us, right? Now, is it clear, guys, for you? Do you have any questions in this part? Yes, everyone. Do you have any questions in this?
Hi, Vipul. Sorry for interrupting. Can you just have 5 minutes break for the Kahoot?
Yes, yes, I saw your message, but just a minute. Let me ask them if if they have any questions.
Yes,
If they
sure.
don't have, we'll go with the quiz. Yes, yes, everyone. Is this thing clear? Okay, excellent. Then we'll have a break for your quiz, and then we'll see the next part, right? So yes, you'll be having a Kahoot quiz now.
Thank you. Thank you, everyone. It's done.
Yes. So what we were discussing is, yes, dealing with the categorical variables. So how do you deal with the categorical variables? So suppose uh, you have a data. Let's say you have car CC, car weight, car year, car mileage, and car country, suppose, right? So as you know, your machine learning model only need to have numerical data, right? So CC is numerical, weight is numerical, year is also numerical, 2015, 2010, 2014. Mileage is also numerical, but country, let's say we have countries like Australia, India, USA, and Japan, and let's say Canada, right? Apart from this, you don't have any countries in your data, but this is not a numerical, right? That is your categorical data. So what do you do if you have categorical data, right? And as I told you in the last session itself, we need to convert your categorical data into numerical by using encoding. It is known as encoding, right? And what is encoding is you convert your categorical data into numerical. So there are different ways of encoding. We have label encoding, we have ordinal encoding, we have uh, one hot encoding. So there are different ways to do the encoding that we are going to see in the next session. So till now we have discussed um, yeah, so I'll just tell you one way how do we go with the encoding column is, let's say you are going with the one hot encoding. So what will happen is, here you will have a country data, you'll have a country data, and here you'll have different countries. Like how it will solve is, let's say India, it will create a separate column for India, Australia, USA, Japan, and Canada. And for India, as this row represents India, so it will be 1 for India and 0 for other rest of the columns. Here it will be 0, Australia is 1, then 0, 0, 0. Same for USA, it will be 1, it will be 0, it will be 0. For Japan, it will be 0, 0, 0, 1, 0. And for Canada, this is 0, 0, 0, 0, and 1. Right? So that is what we have. Is it clear now? So this is how it will solve. And that is known as dummy variable. That is known as encoding or dummy variable. So this is what your encoding is. This is how you do the encoding, right? And after encoding, uh, suppose you, let's take this data only. Um, let's take this over here, dealing with categorical variable. After that, what we can do is we can put a heading as scaling the data. Okay, so this is your data, suppose, right? Now there is one problem associated with the scales, right? This cylinder is having only 1 digit. This is having 3 digit. This is 3 digit. This is 4 digit. This is 2 digit. This is 2 digit. So what happens is, if the all the columns are not in a single range or a single scale, your machine learning will give more importance, more weightage to the column which has higher range or higher scale, basically. So here your weight column is 4 digits. Weight column is 4 digits. It means that automatically your machine learning will give more weightage to this or more importance to this, and it will give least importance to the other variable because that is having less uh, unit or less digits, right? And this particular effect of giving more weightage to a single variable which has higher digit is known as scaling effect. What is scaling effect? It will give more importance to the weight column, right? Rather than other columns. That is known as scaling effect. You need to use, or you need to deal with this scaling effect by using mean max scaling, or you need to scale the data basically by using mean max scaling or standardization. That is also very important part for us, which is known as feature uh, engineering. So I think we have discussed this over here. Okay, that is known as feature engineering, and we'll also discuss that in the next session. So I just introduced the two concepts over here. One is to deal with the categorical variable, we go with the encoding. Second one is we go with the scaling the data, that is by using mean max scalar or normalization. What I will suggest is you can go through this part as part of your homework, and in the next session definitely we are going to discuss this, so you can have this as part of your read, as part of your homework for scaling, and for encoding also you can discuss this. So we'll just take this and paste it over here, this one, right? So that is your two homework. This is what, and this is another. These are the home. You read about this and then we'll discuss this in the next session. All right. So we'll stop here for the day. If you have any questions, you can ask. Otherwise, we can stop here for the day. Yeah. Yes. Anybody have any doubt? Any questions? Okay. Darshini is asking, is the regression line same as the line of best fit? It's not same as the line of best fit, right? We have discussed this point. What do we do is we plot a data and we try to fit a line. This line can be anything. A regression line can be anything, right? But there will be only one best fit line which has the minimum residual sum of squares, right? So we can have multiple regression line, but the best fit line is the one which has the minimum error. So that's the difference between the best fit line and the regression line. Yes, Darshini, is it clear?
Yes, sir.
You can search this, but it's very simple. Like there can be many regression line, but best fit line is the one which has the minimum error, right? Because in this problem statement itself, if you see, we have drawn a regression line, but that is not our best fit line, right? We have to check if we can improve accuracy further or not. Even though that is not something which we have discussed, but yes, accuracy can be improved. You can improve this accuracy by using several ways, but that is not something which we are interested in right now, right? It is little advanced. We'll not discuss that, but yes, you can improve your accuracy, and that improved accuracy. And if you just plot a regression, if you draw a regression line, that becomes your best fit line, right? Yes. Okay. All right, then I'll take silence as a no. We'll stop here for the day. You just go through this and just try to revise this 2 point as part of your homework, which I have given. And then in tomorrow's session, we are going to discuss the scaling part and the encoding part, right? All right, so we can stop here for the day. Thank you and happy learning. Bye.